Yeah, so today we're going to be talking about the Zeroth law of thermodynamics, and that sounds really strange. Why would we make a Zeroth law? Does anybody know why? If you've watched the video already, don't tell me. Do you normally start your laws? Normally, the laws and things like that, rules or items on a list, are not necessarily started at zero. You know, if you're a computer scientist, they are. But yeah. So we're going to come across this a lot. We have the, let's see, why are you not working? Let's click over here. We have these laws of thermodynamics, and they started out with the first law of thermodynamics, and the second law, and the third law, and then they realized, we've never defined temperature. And so we learned that that temperature is foundational to the Boltzmann distribution and all of those kinds of things. Basically, the foundation of thermodynamics is temperature. And so they had to come up with a law that's below the first law of thermodynamics. So how would we track energy? We would track it with temperature. And so when two objects are in thermal equilibrium, they must share a common property. That's just a very generic way to state this concept of temperature. So this property that they share when they're in thermal equilibrium is the temperature. You guys have now got experience in using Boltzmann's distribution and the energy level diagram and the temperature to determine where the probabilities are. But in reality, it's often done backwards. If we have a quantized system, we look at the percentages and we back calculate the temperature. So that's what we're talking about here. When things are in thermal equilibrium, we could figure out that, hey, they both have the same temperature. If we were able to see the quantized systems, we would say, oh, and like the problem on the test, when you have this many levels here and this many levels here, and you figured out the population percentages, then you could solve for that temperature. It'd be easy with that kind of problem to do that in Excel. It'd be kind of tedious with 5 or 6 levels to do it by hand. You might have like in solving for that temperature, a long polynomial with just one equation. And so you might not be able to do it by hand, but you could do it easily in Excel with kind of check and guess. Put in a temperature, does it match? No, change the temperature. And that's what you would do with Solver. So you could put in the whole, partition function and everything like that, and then calculate the percentages of all those levels. And then if you had a spectroscopic measurement of the peak intensities, the areas, that would tell you the percentages of those levels. And then you could determine what temperature it was in Excel. Use Solver until those percentages match what you see in experiment. And it would be a piece of cake. In fact, you could do that for the carbon monoxide spectrum. Remember all of those peaks, the intensities of those peaks? We just used the x-axis, and we determined what the B, the rotational constant, was, and solved for the bond length. But that population of those rotational levels that gives that P and R branch, you could simulate that in Excel, and the intensity is temperature dependent. And so you could solve for the temperature of that gas using Boltzmann's distribution. And so that's if that carbon monoxide is at equilibrium with the atmosphere, then they have the same temperature. So if we get a carbon monoxide spectrum or carbon dioxide spectrum, and we can resolve the P and R branches, then we could determine the temperature of the atmosphere if they're at thermal equilibrium. Okay. And that's one way, spectroscopically, we can measure the global temperature of small molecules in the atmosphere using satellite spectroscopy. And so that's one of the ways to measure the atmospheric temperature on a large scale. The only downside or shaky part of that is the system at equilibrium. Like, is the CO2 at equilibrium with the nitrogen and the oxygen? It probably is because of the number of collisions that they experience. So if the CO2 is a certain temperature, the nitrogen and the oxygen are probably at the same temperature because they're in thermal contact, at least in the lower atmosphere. Okay, then we have the first law. I just have them all listed on this table. We're going to get to each of them later on in this section of the course. Today we're going to focus on temperature, or the zeroth law. So the first law stated the energy of an isolated system is constant. You probably have heard it stated a different way. Energy is neither created nor destroyed, right? And so that's the first law of thermodynamics. And then after Einstein, who showed the equivalence of mass and energy equals mc squared, so energy is equal to mass times the speed of light squared. Now we can say this a little bit more precisely and say mass energy is neither created nor destroyed. So energy can be converted into mass or vice versa, okay? But overall, mass energy, that concept or that item is not created or destroyed. The second law, no cyclic process is possible, which the sole result is absorption of heat from reservoir and its complete conversion to work. So that's a long way to state the second law. And it's what really forbids perpetual motion machines. Okay, there's always friction losses. There's always losses in heat. That we're not converting completely from heat to work perfectly. So efficiencies are never 100%. And that's just the second law in action. It's because the entropy of the isolated system always increases in the course of a spontaneous change. So the total entropy is always increasing. In fact, some people see this as what's driving all spontaneous change is driven by entropy. Statistics, right? If you've got a balloon here that's connected to an empty balloon, and you open the stopcock, that's a whole set of energy levels that aren't populated. And so they're going to be populated, and the gas is going to spontaneously flow into the empty container and populate those energy levels. So there's no way to stop statistics, and that's why things are spontaneous. So we open up a whole new vista of energy levels that are not populated at the thermal equilibrium, and spontaneous change happens. And then the third law, the entropy of a perfect crystalline atomic substance is zero at 0 Kelvin. The practical result of this one is that now we have a reference. We have a reference for zero entropy, and we can make tables. And so this is really the purpose or the function of the third law is thermochemistry, being able to make standard tables of entropy. Okay, so let's go back to temperature, the zeroth law. So this common property is temperature. So remember, the reason we needed the zeroth law is because temperature was the foundation of the Boltzmann distribution, and the Boltzmann distribution was the foundation of all of the other thermodynamic properties. And so that's why I like to introduce that section on the first exam of statistical thermodynamics, because now you understand energy levels from the fall semester. Now you've converted those energy levels into thermodynamic properties. And so you're very comfortable with this statement that temperature is the foundation of all thermodynamic properties. And so let's sort of define temperature. We have a lot of different temperature scales. Are they equivalent? We know that we can write the same temperature in different scales. They have different numbers and different units. But is that all the deals? Why would we call Kelvin absolute temperature? Well, let's look at this little experiment. If we have, say, a container, let's say it's on a piston, we can change the volume and change the temperature and the pressure. So we put a certain amount of gas in a container, we shrink it down to 0.6 liters, and we have it at a hot temperature, and then we cool it down to a cold temperature. We see the pressure drop, and we could extrapolate that down to zero pressure and see what temperature it would be. And if we're measuring everything in Celsius, then we get negative 273.15 Kelvin. And then if we change the piston, okay, and then cool it down, like we make it 0.2, it's kind of strange that it goes back to the same temperature. So this little experiment, I've always wanted to do this to see how accurate, like how precise I could get absolute zero. But it's a pretty simple experiment. You measure the pressure, temperature, and volume of a gas at 2 points in terms of temperature, and you could easily extrapolate that line down to absolute zero. So instead of keeping Celsius as our scale, we kept the same increment. So Celsius has the advantage, it's sometimes called centigrade. Centa means 100 gradations between water boiling and freezing. So it's based on water. So instead of changing that increment, let's keep that. It's a convenient increment. But let's just move zero down here. So that's all that was done for Kelvin scale. It's the Celsius scale, but just with a different 0 point. And so we move it down here to minus 273.15 Kelvin. And so then now that's 0 and there are no negative temperatures. So that's a nice thing too. So as the gases are cooled, you can find the x-intercept. Everything goes to the same thing, and that's been defined as 0 Kelvin. You can do this real easy with a balloon and a bucket of ice water. Okay, you get a room temperature water, put it in there, measure the mark before and after, so you get the volume of the balloon, and then put it in ice water, stick it in there. It should be a smaller volume, but now you've got two data points, and you can make the line and go down to absolute 0. See what you get. So let's take a brief tour of temperature. You know, we live in this wonderful Goldilocks zone where water is liquid, but that's just a small window in terms of temperature. We talked a little bit about the really low temperatures. We can't reach absolute 0, but we can get close with the Bose-Einstein condensates. Remember that little video on that? And helium-3 superfluid, that's kind of an interesting spot, and it's down here. The arrows can't be seen, like 10 to the minus 4 Kelvin. For most liquids, in fact, I would say all liquids, certainly above that temperature, it costs energy to make surface. So if you think about an atom that's happy, surrounded by bulk fluid, let's take water, for instance. I've got a water molecule here, and I'm happy because I'm hydrogen bonding to 2 other water molecules, and 2 other water molecules are hydrogen bonding to me. And so in the bulk, I have 4 hydrogen bonds and some other nearest neighbors. Okay. If you want to make me go to the surface, you got to break some of those hydrogen bonds, because I don't have anybody above me. I've got only bonding partners below me. So it costs energy to make surface, and that's called surface tension or surface energy. Yeah, that's where that comes from. That's why solutions resist making new surface, meaning spreading out. Water will ball up because it costs a lot of penalty energetically for water to spread out. And the reason it balls up into a sphere is a sphere has the smallest surface given a set volume. So that's the shape that has the smallest surface area. So if you spread it out, let's take the extreme, you spread it out to a monolayer, it's all surface area. So that's the worst case. But if water gets something in exchange for that, like if you have a very clean metal oxide surface, it's very polar, and it has a higher surface energy than 72 millijoules per milliliter, then water will spread out as a monolayer because it's coating a high energy surface with a lower energy surface. And so that's how we paint things and coat things, is we want something to spread out and stick, but it's not going to spread out and stick unless that surface it's going on is high energy. Because nature likes to drop energy. Nature likes to roll downhill. So if you want to coat something, you clean it well. Then you put on a lower energy coating and it spreads out spontaneously. It's really hard to get water-based things to spread out. So we add additives like surfactants and things like that. So I've slipped into my cleaning research. But that's why we have this concept of surface energy and surface tension. Energy is an area, surface tension is a line. So they're the same numerically, but they just have different units. Okay. A superfluid has 0 surface tension. So that's kind of a strange thing. If you were to put helium in a container, helium superfluid in a beaker, it would go and coat the whole thing, considering that the beaker has a higher surface energy than the helium. Now that would be a really weird beaker. It wouldn't contain the helium superfluid. It would just coat the surface completely because it has a lower surface energy, a 0 surface energy than anything it touches. And they showed this, they had it in a chamber, okay? So they had it in a chamber, and when they cooled it down, the helium went from being like having a meniscus, by gravity at the bottom to something like this. So the helium was out here. And the meniscus was in the middle. So like this is the air right here. So it went around the walls of the container. So that's pretty neat. So that's a helium superfluid. Then we get up to the average temperature of the universe, very cold. Helium, oxygen boiling here, very cold temperatures. Our area, water. And then we start getting to the high temperatures, okay? And so we can reach millions of Kelvin with nuclear detonations pretty easily. And now we're trying to do that, reach those kinds of temperatures in a controlled manner, because a nuclear detonation isn't controlled. It's very destructive. So we're trying to create nuclear fission and fusion. We do fission in power plants in a controlled manner, but fusion is the next goal, trying to get to fusion. Because when we get up here to million Kelvin, we've got the NIF and the Z machine that are 1.6 to 2 million Kelvin. And that's right at the threshold where fusion can take place. The problem with fusion is, as you get these nuclei closer and closer together, the repulsive effect keeps them from fusing. And so you need extreme temperatures for them to have extreme what? Kinetic energy. So they can hit each other hard enough and be confined enough that the collisions will cause them to fuse. When they fuse, they release an enormous amount of energy. And so we've been like banging against this million Kelvin barrier for years. In fact, when I was a freshman at University of Texas in Austin, I went there in 1987. It seems like a long time ago for you guys, I'm sure. Okay, they had a tokamak reactor in the bottom basement of the physics building in 1987 trying to do fusion research. And they couldn't pinch the hydrogen close enough together for it to fuse. They could get a really hot plasma, but they just couldn't get it to get hot enough. Well, China has claimed this past year that they've made a superconducting tokamak, and that they've claimed to hit 100 million Kelvin. And so that they've maintained solar fusion, if you will, for minutes. And we've barely gotten, like in the NIF, the National Ignition Facility, barely gotten ignition for like a nanosecond or two, maybe 10 nanoseconds. So we've gotten fusion, but we haven't gotten it for very long. Now the Bose-Einstein condensates, again, the bosons are these even-numbered particles, and they're not limited by the Pauli exclusion principle, meaning they can all be in the same quantum state, unlike electrons. You know, you have spin up and spin down, and then you can't put another one in that energy state. And so these guys can get really cold, and we've talked about those. But let's talk about the fusion thing, because that's super exciting. I never understood growing up and learning about nuclear fusion and fission and so on, how it was that you got energy by splitting an atom, and you also got energy out of fusing an atom. Right? Doesn't it seem like opposing each other? It's like, if I split an atom and get energy, how is it that when I combine an atom, I get energy? Right? It seems like I'm given the same answer to two different situations. And it's because the energy in the nucleus is not a linear function. It's a horseshoe, or like a dip, okay? So way out here, these nuclei are unstable. In fact, everything above 82 is naturally radioactive. So we have radioactive versions of bismuth and everything else. And then there's a few weird ones, like technetium-43. Look at that mass on there. Why is it so uncertain? You ever notice that? Right in the middle of the table. It's uncertain because technetium is not a stable nucleus. And so whenever you try to weigh it, it keeps nuclear decaying on you. So we really don't know its mass that well, because we can't get a pure sample of it. You get a pure sample of it and it decays and it's no longer technetium. So that's kind of strange. Look at next to it, look at rhodium. Look how well we know that mass. Very stable. Yeah. But technetium? Yeah, kind of strange. Technetium 99 metastable, 99M is the mass we use for stress tests in the heart. But all of these guys here, you know, all of these are radioactive. Everything above uranium, they say that they're not natural, but there is some evidence that we've had a rock formation in Gabon, Africa, where there was a natural nuclear fission chain reaction going on for many, many years. And so we do have naturally occurring plutonium and americium, some of those things that are made in nuclear reactors, which we thought only happened with mankind, you know, man-made elements, but there's some natural nuclear reactors that we found in mountain formations where they had enough fissionable uranium to go critical and to produce some of these transuranic elements. But they don't get the crazy ones like californium and francium and all of that, and mendelevium.
So they were exploding by themselves?
Yeah, in a mountain. Yeah. Like the uranium was high enough, the uranium concentration was high enough that they started spontaneous fission and they had a little nuclear reactor inside the mountain. Isn't that crazy? Yeah. Google it. It's awesome reading. But anyway, so there's the most stable elements are right in the middle of the periodic table around iron. And so those are the more stable elements. And so if we split one of these unstable elements, we get energy because we're going downhill towards iron. But look below, the lightest elements are even more unstable in terms of if you can fuse them, they make a more stable element closer to iron. This is also what drives stars too. So hydrogen comes together. Now it takes a long time for that much hydrogen to get pulled together, but it accelerates once you get hydrogen attracted to hydrogen in a stellar gas. Then the mass of the whole cloud pulls the hydrogen from further out in, and it gets denser and denser and denser. And the poor little hydrogen atoms in the middle stop having a lot of room to go, and they start reacting, and then eventually the star will light, and you'll get fusion. And when you get fusion, it jumps the temperature way high, and those inner hydrogens can't escape. And so since they can't escape, they're colliding, and then they fuse, and it jumps the temperature up, and you start making helium. And that's a huge jump. Hydrogen to helium, you get that many, joules of energy. It's an enormous jump of energy that it jumps the temperature. Then you get helium. Then you start fusing hydrogen and helium, or helium together with helium, and you just start working your way up. So that's where all these elements came from in the periodic table, is the interior of stars. Yeah.
So for like a star, how come it doesn't stop until the hydrogen is gone, or does it have like a constant flow?
It's I think a lot of it's being drawn in, but it will eventually get too dense and explode, and so you have these nova events and supernova events, and sometimes they pulse, and you have quasars and so on. And I'm not an expert in astronomy, but there's just a lot of crazy stuff that's going on with the stars. So yeah, they do sort of burn out, but they'll explode. They'll get so dense that I don't know what gives them the amount of energy though to explode. So that's a question I still have, is like, what can overcome the gravitational force of all of those stars if fusion doesn't? Right? I mean, we've got fusion going on in there, which is the most powerful reaction we can think of what's causing this thing to absolutely obliterate itself. I don't know. But we can measure the amount of iron spectroscopically in stars and kind of capture its age, because iron builds up in stars because it's such a stable element. Okay.
It just keeps going. Like fusion just keeps going.
Yeah, it starts building all of the elements in the periodic table, and iron starts to grow, and you can kind of look at the spectroscopic emission of iron, or iron absorption in its corona. Like iron gets ejected, it cools down, and then it'll absorb the light as the star is emitting through the gas. We talked about that in the atomic spectroscopy chapter. And so we're able to use spectroscopy to kind of gauge the age of stars from Earth. That's also weird. That's pretty cool. So if I'd have known about this in high school, I probably would have gone into like chemistry and physics trying to do the spectroscopy of stars. When I figured out that was a thing, I was like, oh my gosh, that's so cool. So this is nuclear fusion, this little delta here. And then this is nuclear fission. This is fission, and that's fusion. So we get a huge delta. So here's what's this tremendous energy is known as the mass defect. You've probably never done this, but early on when they were isolating the isotopes of elements, they were adding up their masses, and then they were looking at like if you were to add up, like measure the hydrogen mass, it's just a single proton. Pretty easy to measure, right? And you get that mass out to 6 or 7 decimal places, and then you measure heavy hydrogen. Okay, you've got a deuterium in there with a neutron, and you could take the difference and say that's the mass of the neutron. You could get that out to 6 or 7 places. And then you could take this mass of a neutron, mass of a hydrogen, a proton, and add them up, say, to make carbon, where you got 6 of each. They don't equal each other. So the carbon nucleus does not equal the mass of 6 neutrons and 6 protons. Yeah. Do you get that? Right? It's made up of 6 neutrons. It's made up of 6 protons. But if you add the mass of 6 of each of those, and you don't get the carbon nucleus mass. And they called this mass defect early on. Okay. Where did that energy go? Where did that mass go? I just gave it away. It went into the binding energy of the nucleus. And so if you were to build it, you would put those particles together, and you would keep getting this blast of energy, boom, 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 as you put them all together. And then you finally have a carbon nucleus. And you're like, why are you so light? It's because I gave away a lot of energy when I was fusing. And that's E equals mc squared. That's where that equation came from. That's the missing mass in these things. So let's do this experiment. 2 deuterium molecules slam together, or atoms, 2 deuterium atoms slam together and make a helium-4. All of the mass numbers work out, right? 2 protons equals 2 protons. 2 times 2 neutrons equals 4, particles all together. 4 particles in the nucleus all together. So we haven't lost any particles. Okay. Let's add in the masses of the neutrons and the protons. So this is the mass of the helium, 4.00260202, and this is twice the mass of the deuterium nucleus, and we get this. We get some missing mass. If we run this through Einstein's equation, we get 10 to the 12 joules per mole. That's an enormous amount of energy. So by comparison, this gives us per gram of deuterium, okay, compared to 45 gigajoules per ton of oil. That's crazy. A gram of deuterium is 10 times more energy than a ton of oil. Yeah. And we can get deuterium easily from the ocean. I mean, it's just a naturally occurring thing. We have heavy water. We can isolate that piece of cake. Yeah. Heavy water. Yeah. Like D2O instead of H2O. So the hydrogen has an extra neutron. It's still hydrogen because it has only 1 proton.
Is that like in the deeper in the ocean? Like that?
No, because it's mixing in with water. It's not that much heavier, but it's enough. Yeah.
So
Yeah.
In the ocean, there's D2O and H2O.
Yeah. Yeah.
All in the ocean?
No, it's just because there's so much water there. It's pretty easy to, again, it's a small percentage, and so you just need a big body of water, and then you just isolate it. Yeah, I mean, it's in lakes and rivers and streams too, but yeah, isn't that cool? So we do not, and you'll get this in spades at the end of the course. We do not have an energy problem. We have more energy on Earth. We just have to figure out how to use this one. This one will solve everything. Again, a gram gives us 10 times more energy than a ton of oil. So that's pretty interesting. Okay. So that's why we're really pushing for fusion research. And I'm excited about this Chinese thing. I think that's pretty awesome. But we'll see. I haven't like pulled the thread on it to see if it's true or not. I don't know. It may or may not be. I don't know. But this is the Z machine, and this is kind of an interesting little physics experiment. See these little gold wires here? If you recall electricity and magnetism, y'all had that course, right? E&M, electricity and magnetism, physics 2, I think, right? Yeah. And so if you run current through wires, they generate a magnetic field. Okay, so you got a charged particle going this way. So that's your thumb and a magnetic field. Let's see, make sure, right hand rule like this. And so then that magnetic field sort of, let's call this north, okay? And you run current in the opposite direction here, that's going south. Well, these 2 wires now are attracted to each other. If the current's going in opposite direction, the wires are attracted to each other. So if you run enough current through these wires in opposite directions, those wires are going to slam together. And if you put a deuterium target in the middle, the inertia of those wires hitting that deuterium target may get it to pinch enough to fuse. It's a pretty simple physics experiment, but you need a lot of current. Okay, so much current that you need these ultra capacitors here. And these are all underwater because they would generate so much heat. And just the leakage out, this spider webby stuff, that's like electrical arcs on the surface of the water going to the ground. This is a ladder here. There's a ladder over there. So anywhere there's ground, those charges are going to ground. So a pretty scary looking experiment. But all of these capacitors are all going into this little tiny wire target. And their idea was maybe we can create fusion and get way more energy out than we put in. They have to sip on the electrical grid for like over a month, maybe 2 or 3 months to charge these up. And then they discharge them in just a few milliseconds or nanoseconds. I don't know how fast their experiment is. Think about that, a month's worth of electricity being discharged like that into this target so it slams together and produces fusion. But if you put in 2 months worth of energy and you get 5 months worth of energy, hey, we're still good, right? But that's like in an engine, that's like one cylinder firing. And we need 8 cylinders. We need 8 of these. They fire and we harvest that energy, and then we gear another one up, we fire that, and then eventually it would look like continuous energy on the outside. Like your automobile seems like it's continuous. When you're driving, you don't go, phew, 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 it's lots of little explosions going. Those are not continuous. They're individual events. But because there's so many of them and they're going so fast, we feel like it's a continuous source of energy. Yeah.
So how do you use the energy?
That's the question. So one of Sandia talked about surrounding this whole target area that generates a gazillion joules in a nanosecond. How do you capture energy that fast? And a lot of it's going to be in the X-ray region. Maybe some of it's gamma rays too, because we got a nuclear event. So how do you capture those? Well, whenever we have a nuclear source, let's say that thing was super radioactive, what would I put between me and it? Lead. I would put a high Z element, something with a big fat nucleus, and something with lots of 1s, 2s, and 2p electrons, way deep inside an electron cloud. That's opaque to gamma rays and X-rays. So what does it mean by being opaque? It's absorbing them. So we could surround this thing by a lead container that's designed to melt. And then we have a catch basin below that has a heat exchanger. And then we could boil water into steam, spin a turbine, make electricity. Okay, so that would be a way to capture the rapid event into lead or a high Z element, but lead's the cheapest. It's toxic, but it's cheaper than, it's just in the soil, it's everywhere, okay? So there's no problem getting enough lead. We could have a large lead container and capture all of the energy that comes out of the fusion. It melts, gravity pulls it down, and then we use that heat, because now the heat is in the molten lead. And then we could use that to again, make steam and spin a turbine. We're going to get hit by that 46% efficiency making steam on the turbine. But at this point, we don't have that problem solved either. Yeah. But if we get 10 times more energy we need, we're going to get, 4.6 times what we need out of the turbine. So we're still a huge positive gain. Yeah.
So lead is so unstable?
No, it's not unstable. It is stable. It's very stable.
So it's above lead.
Above lead, yeah. That's why there's so much lead. All of the radioactive elements that blew out of our original star that made our solar system. So our sun is our newest star. So all the planets were made out of the debris from that star that exploded.
Is that what the Big Bang Theory is?
That's even further back. Yeah, so the current time is about 13.7 billion years ago, but our current solar system formed 5 billion years ago. The oldest rocks on Earth ever, like estimated have been 4.5 billion years. So they would say the age of the Earth is 4.5 billion years old. And so, but where did all the radioactive elements came from? They came from a previous star that exploded. And so that previous star produced the thorium, the radium, the mercury, all of these elements that we have on our Earth now. And so many of those were radioactive. Well, they, in 4.5 billion years, have decayed down to lead. That's why we have so much lead. Lead's sort of the reservoir. All these radioactive elements decay down to lead, and then you have a lot of lead.
So lead just has like a really big half-life or something?
Yeah, it just doesn't, it's so big we can't measure it. It just doesn't seem to be radioactive. Yeah, so it just seems to be stable indefinitely. Yeah. So this is the other way to do it, the National Ignition Facility. So this is doing laser confinement. So the Z-pinch is the gold wires pinching the deuterium target. This is using light. So light's going through this and getting this laser is getting super powerful. We did this in the laser section of the fall course, and they hit this tiny little deuterium target here, lithium deuteride. So deuterium and lithium can fuse together and make two heliums. So they hit that target with all this light, and they produce, millions of atmospheres of pressure, and they press it down, and they've gotten fusion out of that. They've actually got positive energy balance on this, meaning the laser energy that went in, they got more energy out. Now it's still tiny, like it's still a tiny little target, okay? And so it wasn't enough to you don't want it to be enough to destroy your whole system and create a bomb, right? But they put X amount of energy in there and it got X plus Y energy out. So that's what they were saying. Ignition, they've made a big press release and everything like that. So I'll do research on the Chinese artificial sun is what they're calling it for when we get to the energy chapter. But these are the hottest temperatures we've achieved. Millions of degrees Kelvin. Chinese are saying they got to 100 million Kelvin, so 10 to the 8 Kelvin. That's incredible. So the deuterium and lithium will fuse and make, let's see, so which lithium is it? It's lithium. I've got the reaction in my notes. I don't have it here. But it's lithium and deuterium get together and form two heliums, I think. Yeah. And it may be two deuteriums and a lithium fuse, and then there's two heliums and a neutron that come out. Yeah. So they can balance, sometimes you can balance the mass particles by having an extra neutron come out. I think that's what happens, yeah. Here's some images of the nuclear detonations. So this is Upshot Knothole. This is one where they did what's called a rapitronic. So this was the fastest shutter speeds that we could capture. So this is the fireball expanding on a nuclear detonation. And so you can see the tower here, sitting at the top of the tower. And of course, the tower, you want to, stabilize it with these guide wires. And so there's these wires that come down. And just like there's a speed of sound through a material, like we're used to the speed of sound in air. If you get underwater, it's a faster speed of sound because water is more dense, and the molecules, the sound waves travel from collisions. And so if the material is more dense, there's a faster sound. Same kind of thing with other shock waves too. And so we can see that these shock waves travel through that guide wire faster than the air burst. So this is the speed of the air, shock wave in air coming out, and this is the speed of that shock wave through the material. So these little spikes are what's going on. Those are the guide wires. Okay. This is a fascinating image because it's so fast. I mean, it's just a few, maybe, gosh, I don't want to estimate, but just a few nanoseconds between each image. What they did was they had a spinning mirror, and they had photographic film here. And so the mirror was spinning super fast, They detonated it, and it was like, gave us these images. And you can see it expanding. What you're seeing is the frontier of the like the thermal wave, and these are emissions. So this is atomic emission from the fireball. It's in the visible region, so it's way over 20,000 Kelvin. It expands at 10 kilometers per second. And the speed is still not fast as the speed of light, right? So it's expanding at 10 kilometers per second, but for light, that's slow. So all we got to do is just capture the image, because light's coming out of this fireball at 300,000 kilometers per second, but the fireball is moving at only 10 kilometers per second. Only, right? And so you can kind of see here it's about to destroy the building that is the base of that tower.
Looks like a giant tower.
Yeah, it's maybe 8 or 9 stories tall. It's not super tall. Yeah, maybe that's 2. I don't know how many stories, but it's not unreasonably high. Yeah. And they just wanted it up there so they could get good images of it. This is all during the nuclear testing days of 1953, so they didn't really understand the way to make these devices, and they wanted to do research too. So that's what they were doing. Okay. So there's some thermodynamic terms. Going forward, I'm so sorry, Q is now something different. It's no longer the partition function. Q is heat. Heat flowing into and out of a system is measured using temperature. So we will use temperature, but Q, just need to sort of set that partition function aside. We're not going to use it again until the final. And so now when you see Q, it's heat. Okay. Heat flows through diathermal walls, and not through adiabatic walls. So there's 2 terms for you. And then heat is an energy system. It can be used to create the capacity to do work. In other words, it can raise energy or lower energy. We're almost out of time. I'm sorry I talked too long on the explosive stuff. Okay. And then we know about endothermic and exothermic. I'm going to kind of go through these. You can hit the video if you need to fill in your blanks. Okay. So again, diathermic is heat conducting. Density is really the key here. So diamond, super dense. So any dense material is a good heat conductor. And that's why our jackets, our coats, our polar fleeces, and so on are not dense, because we want them to be insulating. And so adiabatic walls are insulating. Vacuum's the best. That's why our little Yeti flasks work well. We have a vacuum in there. And so that's why it's super insulating. And foamed plastics. This is a cutaway of a Yeti. This is really good foam permafrost insulation. But the key to a Yeti, your ice lasting longest in the Yeti, is the seal up here. And you've got a tight seal on the lid. Because that heat leak through the lid is where all of the coolers go wrong. So low density is good insulation. And that's it. Okay.